Okay, so my first slide on here, why don't I leave this one till the end? Because we already just did a whole exercise where we had to either name or write down formulas. So why don't we not do more practice and let's get to some of the theory behind this? Because I want to think that if you guys made mistakes on some of these, you probably made the same mistake over and over again. Like say Roman numerals. If you missed Roman numerals, you probably did it like every single time. Okay. So let's get to this flow chart I have right here. I made this a while back as a way to try to help students be able to visualize how you need to name things. And I actually need to throw one more piece onto this flow chart here. But here's the basic concept. First of all, you got to figure out, is it a compound? Okay. There was actually one thing on this Mad Minute we did that wasn't a compound. You remember which one was not the compound? Yeah, oxygen gas. If something is by itself and it's pure by itself, not with combined with someone else's form, that doesn't really fit. Okay, but if you've got like multiple things going together, like A's and B's and C's, like different letters fitting together as a compound, here's a basic concept. The first thing you got to figure out is whether it's covalent, molecular, or ionic. Okay, and hopefully you remember these words, but if not, quick recap. Ionic things typically involve positive and negative charges. So if you have something that's on the positive side of the table and something that's on the negative side of the table, that's ionic. It involves cations and anions. And these guys go through a transfer of electrons where I have one too many, somebody else needs one, and so they give their electron away. I'm going to use a couple of metaphors today to hopefully help illustrate the concept. Imagine we're at the cafeteria. And you know how our special is $6? Well, in the chemistry world, with the octet rule, everything's $8. Can we just change that for a second here? So $8 specials at the cafeteria, octet rule concept. Okay. Let's say that I have $9 and Manya has $7. Can we both get a special? Well, yeah. I have $1 too many. She has $1 too few. So if I just give her $1, then we both have 8. Does that make sense? And everybody wins. So that's more or less what an ionic bond is someone has excess, someone has few, and we transfer. I literally just give it away. And in terms of like valence electrons, I mean, although in the real world you might be like, I don't want to give away my money. Like the things in like groups 1 and 2, they really do just want to get rid of their electrons. They don't want them at all. Okay, so that's scenario 1. Second scenario. It's about sharing instead. Let's say that I have $5 and Manya has $3. I don't have extra, and neither does she, but if we pool our resources, 5 and 3 does add up to 8. Okay, that would be known as the covalent or molecular bonding, where things share their electrons. Okay, now it typically needs to add up to 8 still, but that's actually not a hard and fast rule. The octet rule really works better for ionic compounds. There are so many exceptions in the chemistry world, but in general, those are the two ways of doing things. Someone is either transferring electrons because they're both like this guy has extra, this guy needs more. Or over here, these guys right here are going to share electrons because they're all anions. Anions all need extra electrons. They're not quite there yet, but if they share them, they're good. And they each have different naming schemes. So that's the first thing you got to figure out is which of the two naming schemes do you use? Okay. Now, if it's covalent or molecular, they're actually the easier ones to name usually because you use things like dis and tris in the name. And I got slides on that later, so I'll come back to that. If it's ionic, though, you have to break it up into one of 3 categories. The first category is it just very basic binary 2-piece thing where you just have to do like one portion here that's positive and one portion here that's negative. That's one possibility. The second possibility is what if you need to have a Roman numeral? And so I call those ones the multivalent ones. And there were a lot on this sheet here where there were Roman numerals. So you have to be aware of those because if it needs a Roman numeral, that makes a difference. The last one is what if it involves something polyatomic? And the polyatomics are, if you have your periodic table, you know how there's that little like square written up at the top there? Those are called polyatomics where they come together as a collective group. And they all collectively have a charge. Like say right here, NO3, that's a nitrate. Or CO3, that's a carbonate. Is this ringing some bells here? So I find this flow chart really helps, but if I could add one more thing to it, it would be to have like an extra thing coming off of the covalent molecular ones, and that would be to know your acid names. Because I did throw a couple of acids in there as well. And so I don't actually have it off the flow chart, but if it's an acid, you should give it its acid name as well. That makes sense? So let's go through some notes then on... drop your phone. Let's go through some notes here and talk about each of these kind of, classifications one at a time. So let's start with ionic compounds. I've already given you the analogy of I have 9, Manya has 7. If I just give her $1, we both have 8, right? So here's like kind of a visual picture of this. Sodium has 11 electrons, and there's just 1 electron sitting here in its outer orbital, right? It's got an extra. Chlorine has 1, 2, 3, 4, 5, 6, 7 right there. It really could use 1 more electron in this spot, and then it would be full too. So there's going to be a transfer of electrons happening. And you can see that's what the picture says. So what ends up happening is the sodium now becomes positive because it's now lost its electron, and the chlorine becomes negative because it's now gained an electron. And we now call it sodium, and then the second half of the word, we always change it to IDE, IDE. So I think I have that on the next slide. Here it is. Always write the cation first. So the positive guy goes first, and then the anion, the negative one, goes second, and you just write IDE for the suffix. So oxygen changes to oxide, nitrogen changes to nitride, iodine changes to iodide. So you just got to be really careful with the way you say the end of the word, but pretty much just everything ends in an ide. That makes sense? Now, when you're going backwards and you're working with how to write them, I find that it often helps if I go over here and I use some of these manipulatives. So sorry that you guys have to like look right behind me, but I've got a little mini periodic table right here, and I think this visual kind of helps. If we wanted to do sodium chloride, here's sodium. Fingernails. Here's sodium, okay, and then here's chlorine. And if you know their charges, because you can look them up, sodium is a +1 and chlorine is a -1. Will these ionic positives and negatives fit together nicely? Yeah, right? You have 1 positive, you have 1 negative. So we don't usually write it like this, but if you thought of it as like a math term, you need 1 sodium for every 1 chlorine. But like I'm teaching almost all of you guys math, right? We don't usually write ones. And the same thing in chemistry. If you only need 1 of something, we don't bother writing it. Does that make sense? Okay, but what if I'm using aluminum and chlorine? Here's aluminum. Still chlorine, but aluminum doesn't have a 1+ charge. Do you guys know the charge on aluminum? 3, yeah. So if I go grab one of these guys, you can see that this isn't going to fit together very well, because as I try to piece them together, for every 3+ this guy has, there's actually still 2 pieces missing, right? So the way we solve this is that we need to have more chlorines. Oh, I almost got it. So for every 1 aluminum, you're going to need 3 chlorines. You guys see how that works? Now, sometimes teachers will show you that there's kind of like a crossover where this +3 right here essentially goes there, and this -1 right here essentially goes there. And if you've ever seen that concept, that usually works. There are some times where that doesn't work very well. Like, for example, if you had a 4+ and a 2+, the way it would work is that, let's just call it X 4+ and Y 2+. If that was the case, you wouldn't go X 2, Y 4 and cross these ones over, because 2 and 4, kind of like in math, can be reduced to 1 and 2. So we always reduce it to lowest terms if you can. So, but otherwise, this whole, if you've ever seen that, the crossover concept of like this charge goes on this guy, this charge goes on this guy, that does typically work. Let me try one more off of here. Did I show you guys the manipulatives in grade 12, like these things when we were back in the old building? Okay. Have you guys ever seen something like this with like a visual? Does that help at all in terms of like being able to picture this? Am I making sense? Stop me if I am losing you. I know this is supposed to be a review, but Let's try one more here. What do we got? It's calcium and nitrogen. Wish I had fingernails. So here's calcium. So calcium, if you look it up on your table, is a +2 charge. Nitrogen right here is a -3. Now, nitrogen doesn't usually have a -3 listed, but if you know how the columns work, like the last column's noble gases, they're neutral. Then there's the halogens at -1, oxygen's table's at -2. So long as you know nitrogen's -3, will these fit together? No. Right? So hopefully this helps you visualize it. There's still an extra prong missing here, right? So I'm going to need some more calcium to make it work. Oh, shoot, now I have too much calcium. Okay, well, let's add another nitrogen. Now I have too much nitrogen. You get the concept here? Finally. Everything fits. We have an equal number of positives to negatives. Because really, you get the concept. Okay. So how many calciums do we need? We need 3 calciums for every 2 nitrogens. Or if the crossover thing makes sense, nitrogen was a -3, its charge goes here. Calcium was a +2, its charge goes there. That make sense? Okay. The hardest part is being able to do that quickly, because you got to be pretty fluent at that too. If you're always going back to your table going, what's the charge on this? What's the charge on this? It eats up all your time. And if all your time's being spent looking things up, you don't have time to actually answer the actual questions we're trying to solve. So, you guys feel okay with this then? Let's move on. Okay, well, what if something has multiple valence states? I pointed this out yesterday. A lot of the transition metals in the middle of the table can be +1 or +2. My favorite one is tungsten. If you look at the big table, I had Sam, I think I had him pointed out yesterday. Tungsten has like a charge of 2, 3, 4, 5, and 7. It has a million different charge possibilities. So you have to be aware of which ones have more than one state. Because, like, for example, chromium can be the 2 or the 3 version. So if there's more than one state possible, we need to use a Roman numeral to indicate which one it is. So, like, for example here, Cr2s3, if we kind of reverse engineer what I just did on the board there, if we have 2 chromiums and 3 sulfurs, we need to figure out which possible charge chromium was. Well, every sulfur is a -2, because I can just look that up on the table. So how many negatives do we have? Well, you can see we have a total of -6. Well, if there's 2 chromiums, they each better be the +3 version, because now 6 right here will equal 6 here. But chromium could have been a 2 version. If it was the 2 version, that's not how this would fit together. If it was chromium 2 and sulfur, that would just be CrS, because this guy's +2, that guy's -2. So it actually makes a huge difference which one is which. So the more familiar you become with which ones have more than one valence state, the faster you'll be at knowing whether you need a Roman numeral or not. Does that part make sense? Okay. The third piece to the ionic compounds is we could also throw in these polyatomics. There's not a lot I can add to them other than they're just listed at the top of the table in that little like open square there. And again, the more you use them, the more familiar you are. Thiocyanate, I threw in there. We don't use that one a ton, but you should know things like your nitrates, your carbonates, your sulfates, your phosphates, your hydroxides. If you've heard of those before, hopefully you're fairly comfortable, and it doesn't take more than a second to go look up. You get what I'm saying? So, one quick thought here. Almost all of the polyatomics are anions. They're almost all negative. You've got your NO3 negatives, your SO4 2 negatives, your PO4 3 negatives, your OH negatives. They're almost all negative. There's only one that I know of that's positive, and it's this one right here, the ammonia one. So you don't change the ending of the polyatomics. So you know how all the other things we've been changing them to "ide"? Like nitrogen becomes nitride, carbon becomes carbide, oxygen becomes oxide. If it's a polyatomic, don't change its name. Okay, so don't change a sulfate into a sulfide, because sulfide refers to just sulfur by itself. So polyatomics, if you know them, are actually some of the easier ones to name. Yeah, here I just have what I just said verbally. Don't change the ending. Okay, here's some examples. I mean, not that we probably need to go through these in huge depth, but let's talk through some of them here. NaClO4. So first thought process I'm hoping you're having is I see a whole bunch of letters. This is not binary. This must have a multivalent. Or sorry, must have a polyatomic, right? Because if there were just like say NaCl, where there's just two elements in it, then it's binary. But by virtue of there being an Na, a Cl, and an O, something must be polyatomic. You know what I'm saying here? Like as soon as you start seeing multiple letters together, we must have a polyatomic, so you just need to know which polyatomic it is. So really there's two possibilities. Is there a polyatomic of Na with Cl? Or is the polyatomic grouping the Cl with the O4? Understand what I'm saying here? Like there's only two possibilities. So it's probably the Cl with the O4, which is a perchlorate. Or here, the SO4, which is a sulfate. I gotta point this one out here. Here I've combined stuff together. The CO3 is the carbonate. The Cr is the chromium. But chromium has more than one valence state. So I still had to put which Roman numeral it was. The carbonate is a -2 charge, which means the chromium must be a +2 charge. So I have to put the 2 in Roman numerals here. Does that make sense? Okay, one more thought that I should point out here. If I give you something like, say, beryllium hydroxide needs a Be2+ and an OH-. You're going to need two of these, right? Because this is 2+, this one's a 1-, so you're going to need another one with it. So in a way, you need one of these, you need a second one of these. Don't write it as BeOH2 with the 2 right afterwards, because what does that imply? Just 2 hydrogens, but we need 2 hydrogens, and we also need 2 oxygens. So kind of like in math, when like I do like 2x + 3, this means you have an x + 3, and you have another x + 3, so you really have 2x and 6. Don't forget to like put something in brackets. Only in math, we put the coefficient in front. In chemistry, we do put coefficients in front, but that's for something different entirely. If you want 2 of something, we put the 2 afterwards with a small 2. A big coefficient in front is for when we balance equations, and we'll get to that another day. Sound good? Okay. Okay, why don't we do a quick break here and have you guys try building on what we just did. So I know we did this at the beginning of class. Why don't I give you guys 5 minutes? Here's 10. Try them out. See whether you can write these ones now. Now that you've had a re-crash course on how to do this. Astatine on K should actually be astatide. That should be a D here. That slight change makes a bit of a difference there. Is this coming back to you guys at all? A little bit, no. If I can give some advice, I know I've said over the last day or two that we've been together that none of the assignments that I've kind of got that I've given you so far are really due. But if there's one booklet that you probably just want to do the whole booklet of because it's probably good for you, it would be the second booklet on naming stuff. This is the kind of thing where sometimes it sucks, but the best way to get really good at this is just to do practice, 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 right? The more you practice, the better you get. Everybody, I give everybody like a couple of booklets the first day, right? Okay. And if you don't have one of those, I did post them on the website too, in case you want to get one from there. So, when I'm done the lesson today, it probably wouldn't hurt to just keep practicing, right? Like the more you do it, the better you get. Should I give you guys like 1 or 2 more minutes here? It's hard at first. It really is. I don't. I hope I don't come off as cruel. I don't think I usually do. But I mean, there's 10 here. If it's been 5 minutes, that means you're taking 30 seconds for each one. Hopefully, you guys get where I'm going here. You can't take 30 seconds for each one. I mean, I know that some of you are still, working your way up, but eventually our goal has got to be like 10 seconds or less, right? Like as long as it takes for you to write it, it has to be as long as it takes. Otherwise, you're not doing something. So, I'm not saying that you need to be there now, but we're working. So. But why don't we talk through a couple of these, and then we'll move on. So let me walk you through your thought process, hopefully. As I look at the first one, NaF, the first thing I notice is that sodium and fluorine, one is positive, one is negative, so I know it's in the ionic category. Which honestly, everything we've done so far in the last little while is ionic, but it doesn't have to be. The next thing I notice is that there's not a polyatomic, because if there's a polyatomic, there'd be like 3 or 4 letters there, but there's only 2. The next thought process I need to have then is, does sodium have more than one state? And I just happen to know that sodium's in group 1. Everything in group 1 is just a +1 charge, so I don't have to worry about a Roman numeral. So now that I've kind of narrowed that down, all I got to do is name the 2 things. So Na is sodium, F is fluorine, so it's sodium fluoride. And hopefully that's your thought process, only much faster than I just said it all out. Fair enough? Okay. Second one, I see COSE. Again, I know my periodic table enough to know that there's only 2 elements there. One is cobalt, one is selenium. Because of that, I don't have to worry about a polyatomic. So the next thing I want to consider is, does cobalt have more than one valence state? Now, I got to be honest here, I actually don't know this. So this would be a time where quickly, oh yes it does, a 2 and a 3. Right? And don't get me wrong, I need to look at my periodic table too once in a while. But hopefully that's only for like the, hang on, kind of ones, right? So now that I know that, cobalt has a 2 or a 3 charge. So I got to figure out whether I'm going to call this cobalt 2 selenide or cobalt 3 selenide. So the last thing I need to do to figure that out is know what selenium's charge is. And selenium is a -2. So if I have one -2 and one unknown, the unknown must be +2. So now I can narrow it down. This is cobalt 2 selenide. So change selenium to selenide. Well, it takes a little bit longer to walk through the process. Y and S. One is yttrium, one is sulfur. So this is going to be a yttrium sulfide. But I do got to double check and make sure whether yttrium has a valence state, because when do we ever use yttrium? No, just a 3. Okay. So because yttrium only has a 3 for it, I can just call it yttrium sulfide. I don't have to worry about looking up Roman numerals. Of course, this makes sense. Okay, the next one though pops because I see AGs, N's, and O's. There's now 3 elements there. Something is polyatomic. Hopefully, you're fairly familiar with the fact that an NO3 is a nitrate. So I'm going to have to call this a silver nitrate. But does silver have more than one valence state? No, it doesn't. So I don't have to worry about the Roman numerals, so it's just silver nitrate. Yes. I didn't skip D. And D is what I make the point on. W and I. So W is tungsten, I is iodide, so you think it's tungsten iodide. However, you have to be a little bit careful on this one. Your periodic table, for some reason, only lists 1 valence state for tungsten. What is it? Oh, it does list the 6? Okay. However, the big periodic table at the back actually lists a whole bunch of states there. So on the diploma, they're only going to test you based on what's in the data booklet. So the correct answer would have been tungsten iodide. But it probably should have been called tungsten 6 iodide, because if we look at a good enough periodic table, there's actually a ton of valence states in tungsten. So I put that one on there just to make a point, and I always talk about tungsten over the course of the year, just to point that out to you. But if you just called it tungsten iodide, I shouldn't mark it wrong, because based on the table you have in front of you, that's the information you have. Okay, last one for the first kind of set there. MN3PO34. Okay. First thing that should pop at you is that there's definitely something polyatomic there, right? Because you got way too many letters going on. So you got to go look up what a PO3 is. And is there a PO3 on here? There is not. It's phosphite. And so I've got that on a couple of slides coming up in here in a bit. If you're not aware of how to change the polyatomics, there's kind of a common naming scheme where there's 8s and there's ites. If something is an 8, it has a certain number of oxygens. If it has an ite, it's the exact same thing with 1 less oxygen. Something with 1 less oxygen than that becomes a hypoite. So I have a slide on that later here. But if you can tell that the PO3 is a phosphite, then the only other question is, does manganese have more than 1 charge? And it does. So by the crossover kind of method here, because of that 4 after the phosphate, it looks like it's going to need to be the manganese 4 phosphite. Manganese 4 phosphite. Anybody get that, by the way? Good for you. Well done. Because that involved a couple of things that I maybe haven't even gone through yet. So, memories. Okay, these ones here maybe I'll write down just because it's easier to write them. Going the other way is probably a little bit easier here. Chromium 2 phosphide. I need a chromium. I need a phosphorus. The question now is, how many of each do I need? Well, phosphide, phosphorus has a 3 charge. Chromium has a 2 charge. So I'll have to put a 3 here and a 2 here to make it work. That'll be chromium 3 phosphide. I can start by writing ammonium as NH4 and oxygen there. The question now is, how many of each do I need? Oxygen has a negative 2 charge. Ammonium has a 1 charge, so I'm going to need 2 of them to make it work. Calcium and nitrogen are the 2 pieces I'm working with here. What are the charges? Well, calcium's at 2 and nitrogen's at 3. So I should be able to throw the 2 here and the 3 here. That should be calcium nitride. Okay, this next one here, vanadium. Vanadium is a V, but that's not what this V in Roman numerals is. That V in Roman numerals is 5. That's telling me what charge of vanadium to use. Then chlorite is a ClO2. So the next question is, do I need to put anything in brackets and double it up? Well, this guy is a -1, and this 5 here tells you this guy's a 5. So I'm going to need 5 of those to make it work. So it's going to be V for vanadium. ClO2, which is your chlorite, goes in brackets. Then you need 5 of them. vanadium is a 5, and the chloride is a 1. Did we get that one? Nicely done, guys. Another tough one. Okay, sorry I screwed up the name here. It should never end in I-N-E. That's a mistake right off the bat. It should end in I. So if it's copper 1 acetatide, I'll write it down here. You need copper and you need acetatide. Again, I mean, once in a while I need to look it up. It's AT. Copper's a 1 charge. Acetatide is a 1 charge, so it's just CuAt. Kuat. Okay, the last one, nickel 3 acetate. So nickel is Ni. Acetate's one you might not have come across a whole lot before. Good, you have seen this one before. It's CH3COO. It's one of those polyatomics, and it's a very large polyatomic, actually. There's quite a bit there. Last question, how do their charges interact? This one's a 3. How do I know nickel's a 3? It literally told you there's a 3 right there, right? So we know it's a 3. Acetate's a 1, so we're going to need to put all of that in brackets and have 3 of them. Still with me? Splitting back? Very good. Yeah. Okay. Okay, let's talk about covalent bonds for a bit here. Covalent bonds are ones that sometimes I find that students forget about covalent bonds because we focus so much on ionic that they forget that sometimes it's possible for things to share electrons. And if everything is a negative charged anion, they can actually share. That was the example of I had $5, Manya had 3. We can share to get to 8. Okay. So these covalent bonds, I've already said everything here. So here we go. Here's how you name them. You use a prefix, the first element, a prefix, and the second element, but you change it to I. It just means you need to know what the prefixes are for like 1, 2, 3, 4, 5. So here's a table. Best advice I can give you, if you don't have this memorized, some really smart kid pointed this out to me a long time ago. See how all the groups at the top are labeled from 1 to 18 right here? Yeah, 18. Above 1, write mono. Above 2, write di, tri, tetra. Just write them all on the top here, just in case you don't know what these prefixes happen to be. Someone pointed out that's a really clever spot to write. So when you're naming something molecular then, really the scheme then is use the prefix based on how many there are, and then the name. And then use the prefix based on how many there are, and then the name. This only works though if they're both anions, they're both negatives. Okay? Let me give you a common example of a student who makes a mistake. CuO, no, that's not correct. PbO2. This is not lead dioxide. Because dioxides and trioxides and pentas and that stuff, that is where this guy would be negative and this one would be negative. But if one is positive and one is negative, we have a brand new naming scheme for it. So the dies and tris and stuff only applies if they're both negative. So here's a whole bunch of examples. CO2, you've all heard of this one, that's carbon dioxide, right? By the way, we never start with mono something. If the first one only has 1, we don't bother saying mono. Okay, so like, I know there's only 1 carbon right here, but we don't call it monocarbon for the 1 carbon. We just start with it. But if the second one only has 1, see how there's only 1 oxygen here now? If the second thing only has 1, then we can use mono. So you have a carbon, and then since there's 1 oxygen, monoxide. Or in this example here, see how there's 3 nitrogens and 6 hydrogens? Hydrogen, by the way, kind of behaves. I know hydrogen's way off on like the. If I'm looking at the table up there, see how hydrogen's like way up in the corner there, as though it's on the ionic side. Hydrogen really bonds molecularly more, so hydrogen would count towards like the sharing electrons bit. So I would call this trinitrogen because there's 3 nitrogens, and then for hydrogen, since there's 6, I'd call it hexahydrogen. And then backwards here, silicon tetrafluoride. Well, 1 silicon, tetra, 4 fluorines. Tetra and deca means you need 4 and 10 each. And then di and mono means you need 2 and 1 each. I'm glossing over this bit here. Is that a fair thing for me to do, though? You guys are okay with this bit? Okay. Usually this one's the easier one. You just forget about this, I find. though, that talks about the polyatomic families. All those polyatomics in the top little box there, technically they are bonded to each other molecularly, and then they will bond to something else ionically. So if I ever give you the formula like NaNO3, which would be sodium nitrate, these guys right here individually have a covalent bond to each other. The nitrogen and the oxygen to each other are covalently bonded, and then all of those are bonded to the sodium ionically. That makes sense? So that's why I'm throwing polyatomics now in the covalent column, because we can change those up a little bit. The base level is anything that has an 8 at the end of it, like nitrate, carbonate, chlorate, sulfate. Now sometimes they have 3 oxygens, sometimes they have 4 oxygens, sometimes they have 5 oxygens. There's no rule about whether an 8 at the end of a polyatomic has a certain number of oxygens. This is all about just in comparison. So if you have a less oxygen, call it an ite. If it has 2 less oxygens, call it a hypo something ite. And if somehow it has an extra oxygen, call it a per something ate. Just so I know here. Oh, I don't have any examples. Make up an example. Oh, yeah. I want to do some different ones than the ones that are written, though. Okay, let's make one up here. Let's take a BO3. What's the charge on that thing again? 3 negative. Okay, if I give you a BO3 3 negative, that's on your table. What's it called? Borate. Okay, because it's on your table. You guys can find that one? What if I were to give you a BO2 3 negative? That's not on your table. But if this is borate, then this would become borite. Borate turns to borite if there's one less. If it was a BO 3 negative, it's now a hypoborite. And if for some reason you went, like rather than going down and losing oxygens, some things can actually pick up an extra oxygen. If you had a BO4 3 negative, this would be called a perborate. So if there's really 4 that all go together, we call them a family. So I don't know, like Papa, top dog, is a per8. Then whoever's next is just the 8, then the ite, and then the baby of the family is the hypoite. As long as you can kind of get one of them as a reference, just add oxygens. Quick note though, the charge never changes. The charge does not change. So like a nitrate, a nitrite, all those things there, they have the same charge. Now I don't have a slide for notes on this, I don't think. You should go ahead and name acids. If you have like an H next to like say an NO3, this would have been a nitrate. Well, then its acid name becomes nitric acid, if and only if it's with hydrogen. So 8s turn into X when you're naming them with acid names. But if I were to give you HNO2, this would have been a nitrite. Then we call it nitrous acid. So 8s turn into X, and ites turn into us. I have a silly, silly way of referring this. The first one is that if it's ever an 8, sometimes you say that you ate something icky. So 8s turn into icks. Eat something icky. Whereas for the next one, if you're nitrite, if it ends in ite, if you get into a fight, someone punches you, you might get hit in the gut and go, ugh. Ate, icky, fight, ugh. Anyways, those are only for acids though. Okay, let me try a couple more examples with you here. Let's say I gave you H3PO4. This is a hydrogen with a phosphate. So it becomes phosphoric acid. This is hydrogen phosphate, so it becomes phosphoric acid. But if it was H3PO3, this is now a phosphite. So ites turn into us's, so this is phosphorus acid. H3PO2, this would have been a hypo. So we'd call it hypophosphorus acid. It's also possible to have H3PO5. This would have been a perphosphate. So it just becomes perphosphoric acid. Phosphorus is a weird one because you have to kind of change the endings a little bit to make it sound nice. You guys all learned that at some point before, the ate to ick and the ite to us. There are so many rules for how to name things in chemistry. Eh? Like, I know I drew that tree diagram at the beginning there, but like it's intense, all the little things you need to remember. Oh yeah, and then the last page, I think, right? This is the last one. Thank you very much, you guys. Hold on. I just covered like probably half of chemistry 10 in a day, by the way. Like we spent, at least I know with you guys here, we would have spent like a month on this. I don't know how long lab spent on this with you guys. Like what we just covered in an hour was like a month of that. Anyways, these are some common names you should know. There's other naming schemes that we just haven't learned yet. So, I mean, you guys have probably heard of water. I already pointed out methane and ethane and methanol and ammonia. So, if you don't have them memorized, like I said to whoever asked me earlier, I think Rebecca, like they are in your data table. You'll have that with you. So, if you ever come across a common name and you're like, "Whoa, I don't know what that is," look it up in that table. Okay, that's all I got, guys. Any questions? Russian memories come back. Okay, so here's the deal. Today we have a little bit of time left. Tomorrow, I don't know what's really happening with this whole roundtable thing, whether we'll be in class all the time or not. So, and it's also picture day. So tomorrow's a work day. With whatever time that we do come across tomorrow, I would highly recommend some practice on this. Right? I gave you guys a booklet, just try naming stuff. If you ever want me to mark it, just bring it over to me. I'll look it over. Sound good?